Hi everyone, welcome back to Chapter 2 Thermochemistry. In this video, we are going to talk about Chapter 2.3 Hesss's Law. By the end of the lesson, you should be able to state what is a Hesss's Law, apply Hesss's Law to calculate enthalpy change using algebraic method and energy cycle method. Then, you need to be able to illustrate the dissolution process of ionic solids. So Hesss's law states that the enthalpy change in a reaction is the same whether the reaction takes place in one step or in a series of steps. So referring to the diagram below, from A to B is a single step. From A to B, it can also via a series of steps, whereby you see from A towards X, you have the enthalpy 1, delta H1, X to Y, delta H2, Y to B, delta H3. So the enthalpy for a single step is the same as the sum or the total of delta H1, delta H2, and delta H3 as shown here. So this is our Hesss's law. So there is three methods that we can use to calculate the enthalpy change via Hesss's law, which we can use formula. We can also use algebraic method as well as energy cycle method. Alright, so first of all, let's look at the method using formula. So if you want to use formula, you need to make sure that in that questions, you only consist of enthalpy of formation. These enthalpy formations can be 2, 2, 3, 4, and so on. And only one enthalpy of reactions. So these reactions can be combustions, neutralizations, and it's just a reactions. All right, so a few enthalpy of formations and only one enthalpy of reaction. And make sure that all the thermochemical equations are balanced because we need to use the stoichiometry ratio to apply this formula. So we have the enthalpy of reactions equals to the sum of enthalpy of formations of all the product minus sum of the enthalpy of formations for all the reactants. So product minus reactant. So of course from here you need to have a balanced thermochemical equation. So given in the questions 1, using the following thermochemical equations, calculate the enthalpy, the standard enthalpy of combustions for liquid acetone, C3H6O. And you're given a series of thermochemical equation. So in this case, you need to find the target. Target is what we want and what is the questions asking about. So standard enthalpy of combustions, write down the symbol, standard enthalpy of combustions. You can also write this one as the reaction. Okay, so this one refer to the enthalpy of reaction. And this target, you need to have the equations. For this target, write the equation. So I will show you in the next slide. And let's interpret the equations given over here. As I told you just now, you need to have only one reactions, enthalpy of reactions, and a few enthalpy of formation. So here is your enthalpy of formation. So according to the definitions, when 1 mole of the compound is formed from its element under standard state, so this carbon, hydrogen, oxygens are all the elements at standard state. So this enthalpy refers to the enthalpy of formations for C3H6O. The next equations, when 1 mole of carbon dioxide is formed from its element under standard state. So this enthalpy refers to the enthalpy of formation for carbon dioxide, CO2. The last one, when 1 mole of H2O is formed from its element at the standard state. So the last one refers to the enthalpy of formations for H2O. So you may write down over here, these are all enthalpy of formations. Okay, so for this question, start off with your target. You need to identify what is your target. So target is what you need to answer for that questions. thermochemical equations which are referring to the combustion reactions of acetone. So C3H6O, liquid acetone, when this is combusted in oxygen gas, it will produce carbon dioxide gas and liquid. For the product, because this is a hydrocarbon, so the product will be CO2 and H2O. So if it, according to the definitions, when 1 mole of the acetone is combusted, okay, you will release how many heat? So this is what we want to find, the standard enthalpy of combustions. So balance up your equations. C3H6O, we keep it 1 mole. So we have 3 mole of carbon dioxide, we have 3 mole of H2O, and we have 9/2 mole of oxygen gas. So this is our target equations based on the questions of what we want to find. All right. So according to the equations, enthalpy. So according to the formula, the enthalpy of combustions or enthalpy of reactions equals to the total enthalpy of formations of the product minus the total enthalpy of formations for the reactant. So we need to write in specific together with the stoichiometry ratio. So for product, we have 3 mole of carbon dioxide, so 3 times the enthalpy of carbon dioxide plus 3 times the enthalpy of formations for H2O. So all of these are the product. Okay, all of these are the products and minus the reactants. So we need to minus 1 times the enthalpy of formations for C3H6O and also the enthalpy of formations of the oxygens. But remember about the stoichiometry ratio, 9/2 times the enthalpy of formations for oxygen gas. But remember that the enthalpy of formations for oxygens, because oxygen is the element, therefore enthalpy of formations for oxygens equals to 0. Let's substitute with the value. So 3 times enthalpy of formations for carbon dioxide is negative 394. The enthalpy of water 3 times negative 286 minus the enthalpy of acetone, which is negative 285. And finally, to find enthalpy of combustions, it's equals to negative 1755 kilojoule per mole. All right, so next, let's look at algebraic methods. So for our algebraic method, also first we need to identify the target equations. Remember that target equation is the one that we want to answer, we want to find. So use the definitions of enthalpy to construct the equations needed. And if you want to change the signs of delta H, you need to reverse the equations. So when reversing the equations, you change the sign at the same time. And if you want to change the stoichiometry, so that means if the equations you need to multiply with 2, then you need to change the magnitude of your delta H by either multiplications or divisions. So for example, if you want to multiply the whole equations with 2, the delta H also you need to multiply with 2. So in question number 2, calculate the standard enthalpy of formations of ethanol using algebraic methods. So you are given enthalpy of combustions, carbon, enthalpy of combustions, hydrogen, and enthalpy of combustions for ethanol. So in this case, our target is to find the enthalpy of the standard enthalpy of formations for ethanol. All right, you need to find a balanced equation for this target. All right, so first of all, let's look at your target equations. So enthalpy of formations, for its definition, it says that when 1 mole of the compound is formed, so in this case, our compound is ethanol, keep this ethanol 1 mole. So in this formula, you can see carbon, hydrogen, oxygen. So that means the elements must have carbon, hydrogen, and oxygen. So when one more of the compound is formed from its element under standard state. So carbon standard state is solid, hydrogen standard state is gas in H2, and oxygen the standard state is at O2 gas. Alright, so once you've identified the element, the next step is to balance the equations. Remember to keep the ethanol as 1 mole, as that is our focus. So we balance out, we have 2 mole of carbon, we have 3 mole of H2, we have half mole of O2, as there's only 1 oxygen on the right hand side. So half of the O2, it leaves with only 1 O. And then we want to find this enthalpy of formation. Alright, so next one, we want to look at this information, enthalpy of combustions. So recall back the definitions of combustions. So burning carbon and oxygen produce carbon dioxide gas. So the equation is already balanced. Then we write off the enthalpy of combustions, negative 393 kilojoule per mole. So the second one, enthalpy of combustions for H2. So when 1 mole of hydrogen is combusted in oxygens, it's producing H2O liquid. Okay, because you only got hydrogen and oxygen, so you're producing H2O. So balance up your equations, you got half mole of the O2. Make sure you keep carbon, you keep H2O, you keep your target 1 mole. So we write the enthalpy, negative 293 kilojoule per mole. Alright, the last equation. So when 1 mole of the ethanol is combusted in oxygen, it's producing carbon dioxide and water. So the enthalpy of combustion is negative 1376 kilojoule per mole. So balance up the equations, keep this ethanol 1 mole. We have 2 moles of carbon dioxide and 3 moles of water. We have 3 moles of oxygen on the left hand side. Alright, so the reasons why we have our targets is we need to solve all these equations. So after we cancel off the unnecessary species, we will get back the target equations. Okay, so here if you look at the target, we have 2C. So that means in the first equations, the enthalpy of combustions for carbon, we need to multiply with 2. Okay, we need to multiply with 2. For the whole equations, including the enthalpy. And then after that, we look at this hydrogen in our target. We have 3 molecules of H2. Therefore, for the second equations for the enthalpy of combustions of H2, we need to multiply with 3. And the next one is the enthalpy of combustions. As you can see over target equations here on the right hand side. That means for the equation enthalpy of combustion, we need to reverse it so that we can get the ethanol at the combustion or the product side. So we reverse the whole equations to make ethanol as the product. So as you do this one, the enthalpy of combustions for this species, we need to reverse it. So from negative sign, it will become positive sign. So after we solve this 2C plus 2O2 to produce 2 carbon dioxide. So the enthalpy times with 2. So I leave it like this first to see that, okay, I have already multiplied with 2 in this case. Then the second equation, 3H2, 3 over 2, O2 to produce 3H2O. Enthalpy times with 3. And the last one, we reverse the whole equations to become 2CO2. Okay, change the positions. And then 3H2O. And to produce 1 mole of ethanol and 3 moles of oxygen. So the enthalpy of combustions, we reverse the sign from negative to positive. And after you have got all these equations solved, so now we want to see which species we can cancel off. So first of all, carbon dioxide we can cancel off. 3H2O we can cancel off. And the oxygen, we are having this one. So here you got 3O2. Okay, we have 3O2. So we minus 2 from here, left with 1O2. So this 1O2, after you eliminate this one, 2 over 2 equals to 1. So 3 over 2 is equals to 1 and half. So that means you're remaining half of this O2. So after you get all this unnecessary species cancelled off, then you need to rewrite the equations, whichever species that left. You can see over here, after you cancelling the unnecessary species, you left with 2C, 3H2O, half oxygens, and ethanol, which is the same as the target equations that we have written earlier. Alright, so after you have got these target equations, we just add up all the enthalpy of combustions here. Okay, we add up only to get the final answer. Enthalpy of formations, negative 289 kilojoule per mole. Again, this per mole refer to when 1 mole of the ethanol is formed, this much of energy is released. Okay, 289 kilojoules of energy is released. So per mole refer to 1 mole of ethanol. Alright, so the last method we have here is energy cycle method. So for energy cycle method, also we need to identify what is your target equations. Again, target is what we want to find in the questions. So use enthalpy to construct equations needed. Take notes at the directions of the arrow. So in this example, questions 3, the questions is slightly the same as questions number 1. So you have the enthalpy of formations for C3860, the enthalpy of formations for carbon dioxide, enthalpy of formations for H2O. So again, revise back again. Formations say that when 1 mole of the compound is formed from its element at their standard state under standard condition. So in this case, you need to draw an energy cycle and determine the standard enthalpy of combustions for liquid acetone. So you can see that similar like in your questions number 1, or similar as questions number 1 in which you use the formula. In this case, we want to see using the same questions, how are you going to solve it using energy cycle. So again, target is the enthalpy, the standard enthalpy of combustions. When 1 mole of C3H6O is combusted, heat is released. So the following equations you need to complete it. Okay, O2, and then product is carbon dioxide and H2O, and then balance your equation. Okay, so you can start off using these target equations. You can see C3H6O, you can see carbon dioxide, you can see water. So I choose the easier one to start off. I think that the second equation is simple. So I start off with carbon dioxide. So as you can see over here, we have carbon dioxide as the product in that equations here. Alright, so that means I will produce the product from carbon, solid, and oxygen's gas. Okay, so as you check it back again, carbon plus oxygens to produce carbon dioxide. But in this case, because our target equations, we have 3 molecules of CO2, therefore I need to have 3 carbon, I need to have 3 moles of oxygens. So this equation is considered balanced. So that means our enthalpy over here, negative 394 kilojoule, we need to multiply with 3 times. Alright, so the next one, I go with the hydrogen and the water. So you look at the water, I have 3 moles of water. Okay, I have 3 moles of water. So that means it will be forming from 3 moles of hydrogen gas plus 3/2 moles of oxygen gas. The enthalpy, negative 286 kilojoule. We multiply with 3 also. Okay, we multiply with 3 because the equations over here is only 1 mole of H2O. Here we have 3 mole, so we need to multiply with 3. Alright, so the last equation, the first one, carbon, hydrogen, oxygen to produce 1 mole of C3H6. So as you can see, where madam underlined C3H6 as the product, we have 3 carbon, we have 3 H2O. So what is missing over here? We just add on 1/2 oxygen gas to produce the product C3H6O, your acetone. Okay, so we check it again. Okay, we check it again using the first formula here. 3 carbon, 3 H2, half O2, 3 H2, 3 carbon, half O2 to produce 1 mole of acetone. And for this equation value, which is equals to negative 285 kilojoule. Okay, without reverse, without multiplying anything, so negative 285 kilojoule. Okay, so now I want you to look at this diagram. So I represent the arrow using color following the equations here. So for our target equation, we want to find the enthalpy of combustion. So it's in the directions like this. Okay, from the left to the right. And then the blue and the green color, they are heading to the same directions. And then for number 2 is from this point until this point. Okay, so in Hess's law, the single step referred to here, this S madam put it as the starting point. Okay, and then you see the starting point in just one step, it reaching the end point. Okay, it reaching the finishing point. And then if I want to do in a multiple series of steps, okay, following the arrow number 2, following the arrow number 3. So as you can see over here, 2, 3, 4, the arrow starting from the same point. And then the rest of the arrow that stop at the same point. This point doesn't have stop point because from starting, you proceed until this elbow and then you will still continue until reaching the finishing point. So this is a single step. This is a multiple series of steps. So if you want to look at this, you will see the direction single step and multiple series of steps. So now we want to construct a formula based on your energy cycle. So that means 3 and 4 is equals to 1 and 2. Okay, a single step is the same as the enthalpy change for a multiple series of steps. Okay, so 3 and 4 is over here, 1 and 2 is over here. So now we want to make our equation based on the diagram that we formed. So I label this one is the enthalpy 1, enthalpy 2, enthalpy 3 to make my equation. So enthalpy 1 plus enthalpy of combustion equals to the second enthalpy plus the third enthalpy. Okay, don't forget that in the question is give you standard, so the following enthalpy will put it as standard condition. Okay, so we just substitute the value negative 285 plus the one that we are going to find equals to number 2 is negative 394 times 3. Don't forget about the multiplications that we have written. And the last one, the third enthalpy is negative 286 multiplied with 3. So in this case, the enthalpy of combustions equals to negative 1755 kilojoule per mole, which is the same as the answer in your questions 1, whereby you're using the formula.